Hello, this is a screencast for DSCI 572 Lecture 2 because the university is shut down due to snow. So here we go. We would normally have started with these true-false questions, but we're not actually in the same room, so just going to skip over those for now, and you have them posted on Slack where you can enter them there. So let's just move right past this to the next topic, which is sequences. Let me zoom in a bit to get my usual level of zoom that I'm used to. Okay, this looks good. So sequences. The video you watched before this is about gradient descent, but I think there was a bit of a missing piece in talking about sequences, and this may be old news to some of you, but it will likely be new to many of you. So gradient descent relies on the idea of a sequence, and you've probably seen things like that before, like you have a bunch of x's, and the next x, xi plus 1, is the previous x plus 1, and then you have some starting point, x0 is 0. So in this case, x1 is going to be x0 plus 1, which is 0 plus 1, which is 1, and x2 is going to be 1 more than that, is 3, and x3 is 2, sorry, x3 will be 1 more than that, which is 3, and so on and so forth. So this is kind of a silly sequence because you could have just written x sub n equals n and be done with it, but that's not always possible. You can't always, given this update rule here of how to get the next one, just write down what the nth element is going to be. So also want to point out that some sequences you may have the next thing depending on two previous values. So we, I guess, talked about the Fibonacci sequence before, or you've heard of it. The current one is the sum of the two previous ones, but we can ignore this kind of thing for now because with gradient descent we're not going to have that behavior. We'll just have, however you want to phrase it, the next one depends on the current one, or the current one depends on the previous one. It's the same thing. Okay, so there's this idea of convergence. Some sequences converge, meaning they slowly approach a certain value as you increase I. So the one above doesn't converge. It just goes 1, 2, 3, 4, 5, 6, 7, and just gets bigger and bigger and bigger. But here's a sequence that does converge. The next iterate is the previous one plus 1/2 to the power of I, and x0 equals 0. So I just coded that up. Hopefully I didn't mess it up. Actually, I guess I probably did mess it up in that I should start the loop from 1, x0 is 0, and so on. So we can run this, and we can see that what happens is the sequence is actually converging to the value of 1. And if I just run more and more and more, it's going to get closer and closer to 1. So we say that the sequence converges to the value of 1. And let me just fix this. Okay, so that's the idea of convergence. We're going to need that soon. Next, let's talk about multivariate sequences. So we might have more than one variable, for example, x and y. So at every iteration I, we have an xi and a yi, and then when we update, we need to update both of them. And the next x can depend on the current x, but also on the current y, and likewise the next y can depend on the current x and the current y. So this is just an example. And you can also write this in vector form. So we talked last class about gradients, and sometimes we write f of x, y, z, and sometimes we just write f of x and assume x is a vector. So we could write it in gradient form to say the next x vector is some function of the previous x vector, and in this case we can see up here what that function would be just as an example. So now this function maps from two variables to two variables. It maps from xi, yi to xi plus 1, yi plus 1. So we could code up that function. So here x is a vector, so x0, now this is getting a bit confusing, but x0 refers to this x up here, and x1 refers to this y up here, because we've just taken what we used to call x and y and stored them. Maybe I should have given it a different name, like xvec, but there you have it. So x new, that's this top line up here, is 2 times the old x minus the old x times the old y, and y new is half times the old y plus the old x times the old y, and then I'm going to return the new x vector. So I can start with, for example, x is 1 and y is 1, and I can apply this update a bunch of times and I'll get some values. We don't need to read into this too much, but my point is x and y are updating every time, and we're going to need that for gradient descent. So next we have gradient descent notation. So in the video I had you watch, well, actually we'll get to that in a second, but here's one way you could write gradient descent. The next set of parameters, w, that we're trying to fit or train or learn or whatever you want to call it, are the previous ones minus, and we're doing minus because we're trying to minimize. It would be plus if we were trying to maximize the loss, but we're trying to minimize, minus some alpha times the gradient of the loss evaluated at the current w. So now we're just going to use w for the variables that are iterating instead of x, because we've been using w for the weights in this course. And w is a vector because you could have a bunch of parameters. It's not so interesting if you only have one in your machine learning model. So that's why we just talked about sequences with vector valued states. And then another thing is that you may see this equation written in a bunch of different ways. So sometimes people like to use t as the index instead of I. That's sort of like time. And also because we often already use I to index into training examples, and it's just too confusing if we use I for different things. But also, whether or not we're using I or t, w sub I or w sub t can be confusing in the sense that w is a vector, and when we put a little subscript under a vector, we usually mean that we're indexing an element into that vector, but that's not what we mean. We don't mean the fifth element of the w vector that had 10 elements. We actually mean the whole next w vector. And so in the video you watched, I think I used this notation, where I used t instead of I because we're already using I for the training examples, and I used superscript instead of subscript to not confuse it with indexing into the vector, but instead now we could just confuse it with taking it to the power of t. And so yeah, it's hard to find the perfect notation. Here's another things I've seen before, just using the parentheses, which indicates that you're not trying to take it to the power of something. As long as you understand what it means, it's okay. All right, so gradient descent as a sequence. Gradient descent is a sequence like we just talked about earlier, and we can see it. It's the next thing equals the previous thing, and then some stuff that you're doing to change it. And so just like those sequences before, it needs an initial value, and as we saw in the lab, the gradient descent function, or the SciPy minimize function, requires that initial value. But unlike the sequences we looked at earlier just now, the gradient descent one shouldn't really care that much which initial value you give it, so it should converge to the same solution regardless of the initial value, at least assuming the loss function is convex, which is something we won't talk about too much. But for something like logistic regression, you can expect that if you change the starting points, you might get, it might take longer or less time to run the code, but you should get the same solution. And there's a lot of footnotes and fine print here because there might be multiple global minima and blah, 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 but let's just not worry about that too much for now. So for the stuff we're doing so far, like logistic regression, you could initialize w with 0 or random numbers or whatever, and it should be fine. For other things that we'll do later in the course, like neural networks, it actually matters a lot which initial value you use. And in fact, 0 is definitely a problematic choice. We don't want to use 0, so we'll talk about that more later in the course, but just a heads up on that. One of the many things that make neural networks complicated is that we'll have to be careful about that initial value. Okay, so the idea is that gradient descent, this sequence here that we've defined, was picked carefully so that it converges to a global minimum of f. So that's one way of thinking about it. The other way of thinking about it is that we take a step in the direction of the negative gradient, and so that should be like descending the loss function landscape, and we'll eventually get to a minimum. Okay, so last class we talked about how the gradient is just like a container holding a bunch of partial derivatives, but actually we can also think about it as a vector and the properties that vectors have, like magnitude and direction. So regarding gradient descent, we do kind of care about the magnitude and direction, but what we really care about is the direction, because the direction is telling us which way should I go in order to make the loss smaller. And different optimization algorithms will make different use of the magnitude of the gradient, but all these gradient descent algorithms go in the direction of the negative gradient. So the direction of the gradient tells us which way to go. The size of the step we take, if you look up here, it's actually alpha times the magnitude of the gradient. So if alpha is bigger, you take a bigger step. If the magnitude of the gradient is bigger, you take a bigger step. And so in that sense, we are also looking at the magnitude of the gradient. And kind of conceptually, that's saying where the function is steeper, meaning the slope or gradient is bigger, we take bigger steps. And that, let me just show an example of why that would be a good idea. So so here's just your good old parabola, just for one-dimensional intuition. So if you're way up, the minimum is here. If you're way up here, the slope is bigger, so you're far away, you might want to take a big step. But as you get very, very close to the minimum, you want to kind of take tiny, tiny steps to just refine your solution a little bit to get closer and closer to zero. And indeed, the magnitude of the gradient or the derivative or slope is smaller here, so you'll naturally take smaller steps even if alpha is not changing. Because if you're here, you don't want to take a giant step. You're already close to the solution. You just want to refine it a little bit more. So that's kind of the intuition behind the magnitude of the gradient. Okay, well, we don't need to take a 5-minute break because we're not actually in class, so let's just keep on going. Optimizer syntax. So I wish I had talked about this earlier, maybe on Monday, because a lot of you were struggling Monday and Tuesday in lab with this, so let me try to rectify the situation as much as I can. I asked you to use this function called scipy.optimize.minimize, but I need to say more about what it actually does and how you use it. So this function can be used to numerically optimize functions. So for example, if you have the function f of x equals x minus 3 squared, then we know that the minimum occurs at x equals 3, where in that case f of x is 0, and that's the smallest possible value. So if I just code up that function, I can use this scipy minimize to get me the solution. And okay, there's some small numerical errors here. It's not exactly 3. We'll talk about that next week. But it's close enough. It's returning something like 3, which is what we wanted. And so, yeah, this minimize function, you take a mathematical function that you're interested in, you code it up as a Python function that computes that mathematical function, then you pass that Python function into minimize, you give it a starting point, in this case I just gave it x equals 0, and then minimize will do all the magic for you, and then you call .x, and I'll explain that in a minute. But it's a general purpose. It doesn't work for every function. Again, there's a lot of fine print here, but it works for a bunch of functions. So, as I just said, minimize is a Python function. It takes in another Python function. So in the programming course, we did talk about the idea that you could pass functions into functions, but I'm not sure we had an authentic use of it until now, or at least I can't remember that we did. But that's what we're doing here. And so why do we need to pass f into minimize? Because minimize is going to call f a bunch of times in order to minimize it. And just like the gradient descent function that you wrote calls, well, it actually calls the gradient of f, and we'll talk about that in a second, but it calls the function you gave it a bunch of times, in that case the gradient. It keeps updating w, evaluating the gradient of that new w, updating w again, evaluating the gradient of that new w, so it needs the ability to call the gradient at any w because it keeps changing w and asking what the gradient is there. So it's the same kind of thing here. We had to pass in a starting value, 0, talked about that. Why the dot x? The dot x, so let me remove the dot x and print this out. And you'll see that minimize, so first of all, the type of the thing it returns is this optimized result, so some custom SciPy object. And the optimized result is a Python data type, but it's really just holding a bunch of information. And most of that information we don't care too much about. Okay, it's nice to see that the optimization terminated successfully, that's reassuring. But assuming it did return successfully, what we really want is the solution, and that is stored in the x field, and that's why we call .x to just get the solution, because we want to use that later on in our code. That looks like, oh yes, right. But look at this one, NFEV, number of function evaluations. That's right here, 9. So it's claiming that it called our function f 9 times. And we can verify this by just modifying our function f to add a print statement, saying someone called this function, and now we're going to know. So I'll just run the exact same thing again, minimize f starting at 0. And if you count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, you'll see that it indeed called our function 9 times. So it's not lying here. And in general, it's pretty useful to know how many times your function got called, and you don't really want to print them out and count the print statements. So that is another nice thing that the optimized result object tells us, which is the number of function evaluations, meaning the number of times the code inside of minimize called our function f. Okay, so indeed it called our function 9 times, and that's why we pass in our function. It's just going to call our function however many times it wants at whatever arguments it wants to do what it needs to do. Okay, so why did I just pass in f? What about gradients? This is supposed to be all about gradients. So yes, most of this type of optimization that we're doing is gradient based. So everything I just showed you above is a kind of a sloppy, I would say, use of the SciPy minimize function. And because we didn't pass in the gradient, it was actually trying to approximate the gradient by just calling f a bunch of times. So you could imagine in the one-dimensional world trying to approximate a derivative by evaluating the function at 2 points close together and looking at the slope and saying, well, derivative is kind of like slope. So it has to do something like that. Up until this year, I had a whole lecture about that, this idea of approximating a gradient or a derivative numerically. I canceled that lecture this year because I found it caused more confusion than it resolved. But you can still access the notes for that old lecture at the course README if you are interested. So I'll just say for now that it approximated the gradient. That's kind of sloppy. There's a lot of problems with that. In particular, it'll make the code very slow. And so you should really be passing in the gradient, if you can, to any sort of optimization function. And with the SciPy one, that is done through the jack argument. Okay, so here is my function again, x minus 3 squared. I just took the derivative by hand, just like you were asked to do in the lab question 1. X minus 3 squared, the derivative is 2x minus 3. Here it's just a derivative because everything's one-dimensional, x is one-dimensional, but it will be a gradient as soon as the functions we're dealing with take in a vector. So now I can call in minimize when I actually pass in the derivative, and again, it worked before, but you should really be doing it this way if you can. And here we can. It wasn't too hard to take the derivative. And one thing I'll just point out is that the number of function evaluations is only 3. It used to be 9. And the NGEV, standing for number of Jacobian evaluations, for our purposes, that tells us how many times the second function was evaluated, is also 3. So in total, it evaluated this function 3 times and this function 3 times for a total of 6, and you could say, oh, 6, that's a little better than 9, congrats. But that's really not the whole story. Oh, I see, I was going to do this first. Okay, let's do this first. So we'll do the print statements, someone called f, someone called df, dx, and just see that each one got called 3 times. That's all good, so it's not lying. This is 3, this is 3. this is the right answer. But what I wanted to say just now is that sure, going from 9 to 6 doesn't sound that great, but actually the speed up depends on the number of dimensions, and right now this is all just one dimensional. But if you're optimizing over 1,000 variables, then it's going to be around 1,000 times faster if you pass in the gradient than if you don't pass in the gradient, and that is a huge difference. So you really want to pass in the gradient. And the reason why it's 1,000 times slower if you don't pass in the gradient is that it's trying to estimate the gradient by calling your function 1,000 times. And again, that's all been taken out of the course, and you can look at it if you're interested. But if you're not, then all I really want you to take away from this is when using this kind of function, pass in the gradient unless you have a really good reason not to. Okay, next thing that a lot of people were getting tripped up on in lab. So often we have a loss function like this. This is the loss function for ordinary least squares linear regression that I copied from lecture 1. Here's the gradient of that function that wasn't in lecture 1. I just added it here. Hopefully I did it right. And now what we want to do is minimize this loss using scipy.optimize.minimize, and we're going to pass in both of these. And so now W is going to be our parameters that we're learning. And here's the thing. Minimize is going to call our functions, but it's just going to pass in the W, because minimize is going to be changing W, and for every new W, it wants to call our functions with that new W. So it's expecting functions that only take in W, but these actually take in 3 arguments, because hey, what about the data set? So here's what's going to happen if we I'll make up some fake data set, make up some initial W full of zeros, I'll just naively call minimize, and it's going to throw an error and say, hey, I tried to call fgrad, but it was missing 2 positional arguments x and y, because if I scroll up to xgrad, you'll see it takes 3 arguments x, w, x, and y, but when minimize called it, it only passed in w, because that's what minimize is expecting. So how do we deal with this problem? There's a couple of ways. The wrapper functions and this args keyword, and I'll talk about both. But just note that x and y are staying the same. X and y is our training data. That's not changing throughout the optimization. It's only w that's changing. So that's important for how we address this problem. So here's what we can do. We can make so-called wrapper functions that just wrap the original function. That's why it's called that. So fwrapper only has 1 argument w, and whatever w you give to fwrapper, it's going to use that same w to call f, but it's just going to take x and y out of the environment. So fwrapper will call f with whatever w you want and the good old x and y, the data set, and likewise for xgrad wrapper. And now if we call minimize and give it the wrappers, everything's going to be fine, because minimize is going to try to call our functions. It's only going to pass in w. These only take in w. They'll fill in the x and y, and everything is all good. So that works. People usually use anonymous functions for this because it's just kind of clunky to define fwrapper, blah, blah, blah. So remember anonymous functions from the programming course. So this thing, lambda w of f w x y, is completely identical to the fwrapper up here. It's just we didn't bother giving it a name because we're only going to use it this one time. And likewise, this lambda function over here is completely equivalent to fgrad wrapper up here. And there you go. Everything works. So that's method number 1. Method number 2 is that the people who made SciPy optimize recognize that this is going to happen all the time, and to make your life even slightly easier and not having to use those lambdas, you can actually pass in, you can use the original fgrad, and you can pass in these extra arguments, which the point of them is that when they call your function, they're going to give the w that they want to use, and followed by whatever you give it here. So in this case, x and y. So this assumes that your f and fgrad are set up so that the first argument is w. Otherwise, it's not going to work. Whereas with the lambda thing, you could get around that. You know, if it was if W is the last argument for some reason, then this would still be fine. But when you're using args, you don't have that level of control. So it's assuming that the first argument of f and f grad are W followed by whatever you put in here. And that's pretty much it. So that works. I just want to say I think args isn't a very good name. I think additional args or something like that would have been a better name, because these are the additional arguments or extra arguments that are passed to f and f grad in addition to W, which is going to be the first argument. Okay, so that was the tutorial on scipy.optimize.minimize. Now the last thing we need to talk about today is logistic regression. So logistic regression is a very important topic. It really spans the statistic world and the ML world more than anything else I've seen, which makes it, I guess, both a challenge and an opportunity for us in the MDS program. So in regression 2, you will learn about logistic regression from the statistics point of view. Generalized linear models, link function, maximum likelihood, all that kind of stuff. We're going to look at it from a totally different perspective, but at the end of the day, we're going to arrive at the same algorithm. So one thing we're going to do differently is we're going to encode the target values as +1 and -1, whereas the statistics folks do it as 1 and 0. And this is just going to make the math more elegant, as you'll see shortly. Second of all, we're also going to take more of an optimization loss function perspective rather than the distributional assumptions, Bernoulli link function perspective. Okay, so first a recap of what I think you did in Supervised Learning 1. So to recap, logistic regression is a linear model, which makes it a close cousin of linear regression. Like linear regression, there is one coefficient per feature, or we're calling them weights now, one weight per feature plus an intercept. And we combine the features and the coefficients with the dot product, just like in linear regression. Intercept plus first coefficient times first feature plus second coefficient times second feature. So the output is a weighted sum of the features. And that's why we call them weights, the W's. There is this column of ones trick that you may have covered in regression 1, but if not, you'll cover it tomorrow in feature and model selection, assuming it's not another snow day, that is. But for now, I'll just say we don't really need to worry about the intercept, so let's not worry about it. Going to linear regression, we can write the predictions very succinctly as just x times w. So this is a matrix multiplication, and remember, the rows of x are the examples. And so matrix multiplication, a matrix times a vector, you're going to take each row of x and dot product it with the vector w, and that's exactly what we had up here. So the notation xw is just a super nice, clean, brief notation, and what it's going to give us is it's going to give us the prediction for every example. So this xw is going to give us back a vector of this whole thing for each training example. Okay, so that's nice for linear regression. It's also nice for logistic regression. Next thing to say about logistic regression is that it's a classification algorithm, and it's linear, and it's a classifier, so that's why we call it a linear classifier. The decision boundary is a hyperplane dividing the feature space or the data space, whatever you want to call it, in half. So you presumably saw this in Supervised 1, but you're basically slicing the space in half and saying on one side of the slice I'm predicting positive class, and on the other side of the slice I'm predicting negative class. And the coefficients are essentially a representation of that boundary. So different coefficients mean different slices of the space. We generally use regularization with logistic regression, and that's going to be covered in feature and model selection soon, and so for now we're just going to ignore it. Okay, next thing, probabilities. So when you take W transpose X, you get what that would have been the prediction for linear regression, but for logistic regression it's not quite the prediction yet, and I'm going to call that the raw model output. So the way you get a prediction with logistic regression is you compute this raw model output, this thing that would have been your prediction for linear regression, and then you just check if it's positive or negative. You check the sign. So if it's positive, you predict the positive class. If it's negative, you predict the negative class. And I'll call these the hard predictions, as opposed to the soft predictions, which are the probabilities. Oh, convert the raw model output into probabilities, and now I'll talk about how we do that. So you can take this raw model output, you can just look at the sign and get a hard prediction, but often you actually want a predicted probability out of logistic regression, which is between 0 and 1 and tells you the probability of the positive class. So here's the sigmoid function that you may have seen before, 1 over 1 plus e to the minus x. And here's what it looks like. So what logistic regression does is it computes the raw model output, which could be any number, and then it squashes it through this sigmoid function. So the sigmoid function the output can only be between 0 and 1, and that's because this thing is a positive quantity, and so you have something bigger than 1, and then you take 1 over it, gets you something smaller than 1 and positive. So you have this squashing process, and here's the beauty of it. I just said before that 0 is the boundary for the raw model output, that if it's positive we predict +1, if it's negative we predict -1. But look where 0 corresponds to here. 0 corresponds to probability 0.5, so that really makes sense, because if the raw model output was positive, you would have predicted the positive class. The probability is going to be more than half, and so it makes sense. When the probability is more than half, you predict the positive class, and when the probability is less than half, you predict the negative class. And you can also look at this function in kind of different zooms. So if we look at it like that, you can see really the kind of squashing effect. I just changed the range that we're plotting. Okay. So we talked about that. We can interpret the output as probabilities. So yes, probabilities are between 0 and 1. We all agree on that. So this function turns the raw model output into a probability. It is a monotonically increasing function, which makes sense. So bigger W transpose X means more likely to predict class 1. So we talked about that. We talked about that. Okay, so that's all the prediction part. Predict. And so scikit-learn calls it predict probo when you want to predict probabilities. We talked about that. Now we want to talk about the loss or fit. So as I said earlier, I'll leave the maximum likelihood type discussion of the loss to regression 2, and instead we'll take a different perspective here. Oops, squared error, sorry. Okay, so this was the loss for linear regression. F representing the loss, f of w, because it's the weights that we're changing, is the sum over all my training examples of the prediction, which is the weights dot product, the training example, minus the true thing squared. So we can't really use squared error for logistic regression because the y values are only +1 and -1. So for example, if the raw model output is positive 1000, and the true class is 1, that means you got it right, because positive 1000 is positive, so you're going to predict 1. The true class is 1, that's all good. But according to this loss, that's a horrible prediction, because the squared difference between 1000 and 1 is huge. So it just doesn't make any sense to compare the raw model output, which could be any number, to y, which could only be 1 or -1, and call that your loss. So we're not going to do that. So what we need instead is a loss that encourages the raw model output to be positive when the true class is positive, and encourages the raw model output to be negative when y is negative, and that way when we train we're going to encourage the thing to get the answer right as often as possible. So now here's the fun part. Consider multiplying y by the raw model output, and this is why we encoded the y values as plus or minus 1 instead of 0 and 1, because we can play this elegant trick. When we multiply these two things, this quantity is something we always want to be positive. Oops, sorry. Where did that go? Here. we always want this to be positive, because if y and the raw model output have the same sign, that means you got it right, because the true class is positive and you predicted positive, or the true class is negative and you predicted negative, you got it right. Whereas if they have the opposite sign, then you're wrong. And here, if they have the same sign, this will be positive, and if they have opposite sign, this will be negative. So this is really kind of the key trick here. It's just kind of mathematical trickery. But if we multiply these together, we can say we always want this product to be positive, because if it's positive, it means they have the same sign, and if they have the same sign, it means you predicted the right class. So we want a loss sort of like this. This is not the real loss, but just conceptually we want a loss that says, let's go over all training examples as usual, but let's put a minus sign here, because by convention we're always minimizing the loss. So minimizing something negative is the same as maximizing this. And now we're just saying, yeah, try to make this thing positive or maximized all the time, and then we're telling it to make correct predictions. So minimize this whole thing with the minus sign, or maximize it without the minus sign. Either way, we're just trying to get the answer right for all training examples. This is not actually the loss we use. It's not going to work. I think it's probably going to cause the W's to go to infinity or something crazy like that. But what we have instead is this. This is the logistic regression loss. It looks a little more strange than this one above, but it is roughly the same idea. So the key idea that we wanted is that we want minimizing the loss to correspond to making this product as positive as possible. And so let's plot this function. So here it is. Log 1 plus e to the minus z, where z is this thing over here that we want to be positive. Okay, here's our picture. So here's y w transpose x. Again, this is the thingy that for an individual training example, we would like it to be as positive as possible, because that means that these two are going to have the same sign, or encourages yi and the raw model output to have the same sign. And all I really want you to see from this picture is that it's going down, and that's good because we're trying to minimize the loss. And so by minimizing this, making it smaller, we're moving to the right, which is good because that means making this positive, and we just said that making this positive is what we want. So it's kind of a hand-wavy argument. All I'm really saying here is that if we minimize this loss, then it's going to try to make this thing small for every training example, because we're summing over training examples, which corresponds to, in order to make it small, you need to move down this graph, which also means moving to the right. And so all I'm really saying here is that minimizing this loss, I'm trying to convince you that minimizing this loss corresponds to encouraging it to get the right answer. And I'm not saying this is like the perfect loss, but I'm saying it should get the job done and be reasonable, and I think that's all we really care about for now, and then you can talk about the statistics interpretation separately. Okay, a major confusion warning. Earlier we talked about the sigmoid, which was this thing, which squashes the raw model output into a probability. Now we talked about this function here, log of 1 plus e to the minus x, which we used to turn this thing into a loss. So these look almost the same. I mean, you can look at them. It's just changing a log for a 1 over. And so I think a lot of people get confused between these two things. But while they're only slightly different mathematically, they're completely different in their role in this story. So the first one, log of, I guess I reversed the order, sorry about that. The first one in this list, which is the one we talked about most recently, maps this clever product y w transpose x to some positive number. You can see it's some positive number. And it then becomes the loss contribution from one training example, because remember, we're summing this, sorry to scroll, but we're summing this over all training examples. So that inner thing is the contribution for one training example, and to get the overall loss, we're summing over all training examples, which is something we always do. And so this is for fit. This is about the loss. The other one, 1 over that thing, maps the raw model output, there's no y here, to a number in 0, 1 to be interpreted as probability, and this is used in the prediction phase to predict a probability. And indeed, notice this one doesn't involve y, because when you call predict, you only use the coefficients in x, right? You don't use y when making a prediction, you only use y during training, so it makes sense that this one is used in something involving y and has something to do with fitting, and this has something not involving y and has something to do with predicting. So actually I kind of feel bad about using x here, because that's not the x of the data set, it's just some generic, maybe I should just say z, even though it'll be kind of boring to watch me fix this. I just want to make clear it's like some generic variable, that, and this is just a generic function, not the x from the data set. So there we go. Yeah, so like up here I used z for my lambda. Okay, so yes, major point of confusion for logistic regression, I think, and hopefully that could clear things up a little bit. Moving on, error versus loss. We're almost done. So when you talked about things in supervised learning 1, like random forests, it was all about accuracy, or error rate, which is just 1 minus accuracy. So I got 75% accuracy or 25% error. It doesn't matter which one you want to say, they're the same thing. But with logistic regression, and some other methods that we'll start talking about, there are now 2 different metrics that we need to juggle in our minds, the error and the loss. So scikit-learn score returns the accuracy. I'm making a scikit-learn logistic regression. I'll just turn off the intercept for now for simplicity. I will fit it on some random data that we had earlier. We can ignore the warning. Call score, and it says 56% accuracy, so 44% error. The loss, though, is not 44%. The loss is something different. And in fact, here's the code from lab 1. I just copied this code over. And now I can call this function on what I have. So the W, I'm just extracting the coefficients from the scikit-learn logistic regression object. And then I have my x and y. And my loss is 66. So it's not a percentage. It really has nothing to do with the 44% error, except that you kind of want the error to be small and you kind of want the loss to be small, but they're different. And actually I had some stuff I was going to say later, but let me say it now. Why do we have these 2 things here? Well, we can't just directly minimize the error, also known as directly maximizing this accuracy score, because of the way the optimization works, which is that this, when viewed as a function of the weights, this score is not a smooth function. So basically, as you change the weights, it's going to suddenly get another thing correct, and so that's going to be a little jump in the score, and then you'll change the weights some more, and then the score will stay the same, and then suddenly you'll get something else correct, and the score will jump again. And so that you can't really use optimization methods effectively on that. You kind of want to smoothly find the minimum of the loss using something like gradient descent. So this loss, on the other hand, if you change W a little bit, it changes a little bit. And we could even do that experiment. You could even take W, just change it a tiny bit, and you'll see you'll get the same score, but a slightly different loss. Okay, moving on. So this thing I just put in your lab, and had you believe me that it was the right thing, I just wanted to show you. Scikit-learn.metrics has the logistic regression loss, and I can call it using my same object, and I had to get the arguments just right, but you can see it's doing the same thing. So this number comes from the code I gave you in the lab. This number comes from scikit-learn's logistic loss. They're the same, so that's just a check that the code I gave you in lab is hopefully not wrong. So that is good. Now this stuff, oops, another typo. This stuff here is what I just talked about before. So you have to have the error rate and the loss simultaneously, because the error rate is kind of the thing that you care about. It's how many did I get right and how many I get wrong. But you can't directly optimize it easily. So the loss is like a proxy for how well I'm doing. And that's what we were just talking about for the last few minutes is, well, it makes sense when it's smaller, things seem better. So that's kind of a good proxy. But it has the properties that make it amenable to minimization algorithms like gradient descent. And so we directly minimize the loss and hope that it minimizes the error rate at the same time, which it more or less does. So that's all for the lecture, I guess. Since this is a screencast, I can just quickly touch on this optional stuff. All I really wanted to say is that in this discussion on the data space and the parameter space that you saw in the video, I just want to give a different example of what those could look like. You feel free to turn it off and not continue watching if you're not interested, but I'll just quickly talk about this to say that I can do an example of a linear regression with no intercept. And so here, before we had a thing like this on the left and some contours on the right because we had two parameters, the slope and the intercept. And so we had to draw the loss as contours, as like another dimension coming out of the page. All I'm really trying to say here is that there's no reason why the dimensionality of the data space has to equal the dimensionality of the parameter space, and indeed they'll be very different with neural networks. So here I kept the data space the same as in the video you watched, but I changed the parameter space by removing one of the parameters, and now I just use a different type of visualization, just a regular plot of loss versus the only parameter, as opposed to the contour plot, and you'll see other examples coming up in feature and model selection as well, where the parameter space is going to be much higher dimensional than the data space. And that is it.